Which is the stronger acid? Why is H3O plus the stronger acid?
Because oxygen doesn't want that positive charge to stay on.
Okay, so we've got a couple ways to approach this. One is just saying, well, oxygen's charged and it doesn't want to be charged, particularly positively charged. Okay. The pseudo-official way is to remove a hydrogen and see what happens. We'll be looking at H2O and H plus versus, in the other case, OH minus and H plus. Well, according to our rule set, so number one, we want to eliminate the thing that stays the same. H plus stays the same in both cases, so that's irrelevant to compare. So what I really need to compare is the H2O versus the OH. And what I'm looking at are the conjugate bases. Okay? Well, all reactions strive to minimize charge. So in this comparison, which of those reduces the charge? H2O. So H2O is the more stable conjugate base, which then makes H3O plus the stronger acid. Okay. Why? Well, our explanation goes back to minimizing charge. Okay. And said better, which we had previously, and of course this is not the slide I want it to be, but I won't fix that. We should just be looking for charge. So the rules that we've got listed here are generic rules. They aren't our perfect apply only to acids or apply only to bases. These are the generic rules that can be applied to both. We just have to make sure that we're evaluating our definition appropriately. Okay, so now let me fix this again and just say we're looking at charge. Okay, what if we'd switched to our base analysis? We could say OH minus versus H2O. That was kind of boring. God, don't push that button again. Let's try that again. Let's do NH2 minus versus NH3. Which is the stronger base? NH2 minus. Why? But didn't we just say we want to minimize charge? Isn't...
By gaining it.
We've changed our definition. In the previous cases, to minimize charge, what were we looking at? An acid. I'm not being asked to compare acid strength now. I'm being asked to compare base strength, which means the fundamental analysis has changed. Okay? When we look at acids, we go to looking at the product. We look at the conjugate base. We could do that for our bases as well, and we could evaluate the conjugate acid and decide which is stronger. If we go through to react these, I'd end up with NH3 with a lone pair. In the other case, I'd end up with NH4 positive. Which one has the smaller charge?
NH3.
NH3. So I can still use that minimal charge, but where am I looking in this case? I'm looking again at the product. Do I have to evaluate the product in the case of the base? I would argue no. I can look at the reactants. Why can I look at the reactants instead of the products when I'm looking at the base? When I'm looking at a base, what am I looking for? Negative charge. I'm looking for something that can donate electrons. Well, everything we do with curved arrows shows the motion of electrons. I'm already in the state that I can now compare and do my evaluation. When I'm comparing acids, I'm not looking at electrons, I'm looking at the ability to lose a hydrogen. Well, they both have hydrogens. How do I know its ability to lose that hydrogen? Well, I remove it, and then I can evaluate. So I end up looking at the base. Okay, so I end up looking at the conjugate base when looking at acids. And when I'm looking at bases, I look at, well, the base. I don't have to look at a product. Okay? But it comes from my perspective on what I want to go through and evaluate. Does that kind of make sense? Okay. In both those cases, what did we compare? We used charge as our explanation. So let's switch it up and move to the next one. An atom effect of size. Let's compare Br minus to OH minus. Because I want to do a size comparison here, notice that what's the deal with the charge? It's the same in both. Because if the charge was different, then I wouldn't be looking at an atom effect of size. I'd be comparing them based off of charge. Okay, so what we're starting with is our charge is our largest definer of our acids and bases. And we can then move through subcategories when we don't have that thing to compare against or when they're the same. So when we now look, we do have a size difference. How does that affect our reactivity? So number one, should I be looking at acid strength for these two compounds? We do a versus here. Why not? So they're both negative, which already suggests not an acid, because acids typically are positive. Why are acids typically positive? What is our definition of our Bronsted-Lowry acid?
Proton.
A proton donor. So if we have negative charge, we're likely not to donate a proton. The whole reason why that molecule is unstable is because it has negative. By donating a proton, I'm becoming more negative. That goes against the whole premise of our reactions. We're making it more charged. We're trying to minimize charge. Another big reason why we should not be looking at acid strength here. What was the definition of a Bronsted-Lowry acid? A proton donor. Take a look at bromide for me. Said artfully, it ain't got no protons. Exactly right. There are no protons there. I can't be evaluating acid strength because it's not an acid. It doesn't fit any definition of acids. Okay? So I can be evaluating base strength. Okay? In that comparison, I could look at the stability of the conjugate acid. But again, conjugate acids are not the easiest things to compare. If acid strength was easy to compare, we wouldn't be looking at evaluating the conjugate base for acids as a definition. So we can look at the negative charge. Which of those negatives would be most likely to act as a base? Okay, I heard bromide. Too late. What are we trying to do? To act as a base, what must our negative charge do? Here, lose, attract a positive, accept a proton, donate electrons. Where are the electrons going with respect to the atom? Away from the structure. If the electrons stay in the structure, it is by definition not acting as a base. So if the electrons leave, we're looking at a base. Okay? What is going to make those reactions more likely to leave? So we could look at electronegativity. Unfortunately, what's the electronegativity going to do for us here? It's going to bite us in the butt, because when do we look at electronegativity? We have to look at size first. We could try and do electropositivity. How many people have seen a table of electropositivity? Okay, so nice idea. In theory, it fails in practice.
Does it go to resonance?
Resonance, not a bad idea again, but that's further down the list. What should we be comparing? We started the whole process off. Size. Right? They both have the same charge. We need to look at size, the ability to share those electrons with something else. How does size affect that ability? Right? Well, they both have an extra pair of electrons floating somewhere in their structure. In the case of bromide, those electrons are floating in a very large area that is supposed to be spherical. And in the case of oxygen, where are those electrons floating? A very tiny area. Right? If you're trying to play tag, where is it easier to play tag? Okay? And one of those little baby playpens, sorry, that's all I got as an example. Okay? Or a football field. Probably the baby playpen. It's also going to be a boring game. Why? They're closer together. It's really easy to just tag back and forth. When we look at the smaller atom, those electrons are now pinned in one location, which means if I have another atom come by, more than likely, what does that atom interact with? Those electrons, and it does a reaction. In the case of the bromide, the electron or other atom comes by near close enough to it, but those electrons, odds are, aren't nearby to react. We don't get a reaction. Okay? So size has an effect on our reactivity. So in this case, we would say which of those is the most basic? The OH. Okay, the OH is most likely to share those electrons. Okay, as a simple fix, I'm not quite sure it's a fix, but let's look at another modification. Let's now compare HBr to H2O. Which is the stronger acid? HBr. And you know that because? I can almost guarantee I know why you know that.
It's a strong acid.
It's a strong acid. Because some jerk off in Gen Chem said there's no point in explaining. It wasn't written, so it's okay. Shoot, I think it closed captions. So it is kind of written. Distractions. Acid-base strength. We're talking about acid-base strength. Okay. You know it's, oh, I remember, because I was calling names of people. Bad people in general chemistry have decided to not go through and explain all of these rules. They decided it's easier just to say, well, students memorize this. Memorize that HBr is a strong acid. Well, why is it a strong acid? That's what we must evaluate now in OChem. Well, is it charge? No, they're both neutral. Is it size? Well, in both cases, it's H+. Is H+ a different size? No. So we go, well, I don't see a difference. Where's that difference? That's why we evaluate the conjugate base. I try and draw a structure that makes the difference most apparent. And when I do the reaction, I can see that I have a large difference between Br- and OH-. They're now negatively charged. They are reactive. Which of those is less reactive? Bromide is less reactive. So what does that mean about the acidity of the parent compound? The one that I actually asked the question about. Careful. Our bromide is more stable, which means what is the likelihood of that reaction happening? More or less likely? It is more likely. Man, you guys keep alternating each side. One person says, oh, it's this. And I go, oh, let's fix that. And then as soon as I do that, everybody on the other side says the other thing. Okay. If we're looking at those two reactions, 1 and 2. In purple, I said bromide is more stable. Okay, what does that mean about the likelihood of reaction 1 in comparison to reaction 2? It is more likely to happen. Okay? We aren't saying it's going to happen. That's a separate comparison. We're just saying more likely at this point. It is more likely than reaction 2 because I form a more stable product. More stable products always form because what did we do? We minimized the charge better than the other one. So if reaction 1 is more likely to happen, which of our compounds in the red box are more acidic? HBr is the more acidic one. How do I know that one is more acidic? Well, what is HBr more likely to do? Form products. And in the formation of the products, what did it do? It released the proton, like the Kraken. Yep, Br- is less reactive. And you might say, well, isn't that the opposite of what we just did? Didn't we say Br- was less reactive in the last one? Yeah, we did. So why did it all of a sudden appear to switch? It didn't switch. It's the exact same explanation. What switched? The question. The question changed. We went from ranking acid strength or base strength to acid strength. This is why it is of critical importance to know your definitions. If you take a look at the practice exam, you'll notice the practice exam has a couple questions in it that say, define a Bronsted-Lowry acid. Okay. That question is there kind of as free points, and it's also there as a reminder. I now know that a Bronsted-Lowry acid must do this. So when you get to a question where you're asked to rank acid strength, you can look back at your definition and be like, oh, that's what the definition was. I must use that definition. Okay? And I'll give you a brief warning on this. If enough people get it wrong, it will show up again. Shoot, I can't ask it again. It'll show up again on next semester. Okay? And in next semester, it won't be points. It'll be a loss of points. Right? If you don't know those definitions, you don't know organic chemistry. Because that's what we're doing, is we're applying those definitions. Okay?
So in this class,
in this class, we aren't ignoring the Lewis acid-base definition. We still use it because Lewis acid-base applies to everything. We just choose to not label things typically as Lewis acids and bases because that applies to everything.
what textbook have you?
The textbook shows it everywhere, and they will ask questions in Smart Work about it as well. Okay? Primarily because they want you to be aware of that definition. It's not wrong. It's perfectly valid. And when we talk about Bronsted-Lowry, we are talking about Lewis. Okay? The issue is what happens when we talk about nucleophiles and electrophiles. Well, those are Lewis, not Bronsted-Lowry. Okay? So if we call everything Lewis, well then how do you know if it's a Bronsted-Lowry reaction, acid-base? How do you know it's not a Bronsted-Lowry? You would have to then say it's Bronsted-Lowry acid-base. Not just, oh, it's acid-base. What does that mean? Yes, I am inherently lazy. I do not want to say Bronsted-Lowry every time we talk about an acid-base reaction. Okay? It is just dumb. Lewis is just too broad of a definition. That's why we have nucleophiles, electrophiles. That's why we have our Bronsted-Lowry acid-base definition. You need to be able to apply Lewis to all of those. But it applies the same in both directions. Okay? So I said it was going to be a quiz, but I lied. Yes, 10 out of 10. What I want you guys to do is spend the next couple minutes, because we just looked at an example for charge, we looked at an example for size. The quiz question is down here, so we won't make it an official quiz, but we'll make it an unofficial quiz. By unofficial, pick two structures, rank acid-base characteristics according to hybridization. So you will now say this one is more acidic than this one because of this hybridization. When it's up on the board correctly, I'll give you points on the exam. And we'll give you 2 minutes. If we were to compare acidity between these two structures, what do we need to do? Draw the conjugate base. So if we draw the conjugate base, draw this conjugate base. I'm not going to show all those stupid hydrogens. What are we comparing? The stability of those two structures. Charge. Is there a difference in charge? No. What's the atom holding the charge? Carbon, in both cases. Is there a difference in size? No. Is there a difference in electronegativity? Okay. We'll come back to that. Is there a difference in resonance? So the resonance that we must show would be stabilizing the negative charge. We can do other resonance. We can do all sorts of other stuff to make it resonate. Okay? You could have one crazy person leading the country and a bunch of sane people controlling said crazy person. Everybody's going to go, oh, that country's full of crazy people. Okay? It doesn't matter about the side effects. It matters what's the primary focus. Okay? So our primary focus is on that negative carbon. If there's other resonance out there, I don't care. It's got to be dealing with the negative charge on that carbon. Okay? There is no more resonance on that negative carbon. Is there an inductive effect? Okay? This is where we'd go, oh, crap. Okay? But I can't put that in writing. So everybody's going, oh, what's the carpet? Just doing a little letter swapping, right? Because we've exhausted all of the easy explanations for acid-base characteristics. We now have to evaluate hybridization. And hybridization is not a fun one. Okay? Notice that hardly anybody drew any, even after the hint, you drew anything, nobody really added anything extra to it. In fact, I heard people comparing, well, methyl versus ethyl. You didn't change the hybridization. How many of you remember hybridization? That's kind of an important topic. This is where it comes into play. Okay? How does hybridization affect the stability of those negative charges? Well, as is explained up on the board, we're looking at S character. If we are less hybridized, the sp character of our alkyne means we are more S. Okay? sp3 means less S. What does S character have to mean? S character in comparison to P character. Well, what's the difference between S and P? S is lower in energy. Why is it lower in energy? It's closer to the nucleus. So the more S character you have, you are effectively holding the electrons tighter. Oh, that kind of matches the definition of electronegativity. The sp atom has a higher effective electronegativity than the sp3. With that information, what does that mean? We can go back to our chart. We can look at charge and size. We're really doing an atom effect comparison based off electronegativity. Which atom is more electronegative? Well, the sp one, which means it can stabilize the negative charge better, which means acetylene is more acidic than an alkane. Okay?
Does the bond length have anything to do with it?
You can bring bond length arguments into it. I don't think it's worth the trouble. Yeah. Yeah. You could, but how many people evaluated hybridization under the electronegativity category?
I'm just saying as you got
Yeah. So really what ends up happening is are there more rules than this? Yes. And there are almost always an application of something above, but some nuance. Oh, you have to use molecular orbital theory to explain this one. Oh, you have to use hybridization. And yes, they are more nuanced, but they're really just applications of the earlier ones. Okay? And really, is size really all that important? If we just say minimize charge, aren't all of those rules really just saying minimize charge? Yeah. So we really don't need any rules, we just need one, minimize charge. Okay? So we're kind of subdividing as we get into those nuanced aspects. Kind of make sense? Okay. So as a highly encouraged that you memorize, those 5, 6 rules are things that you should have committed to memory. Because every time you run a reaction, you will be like, well, I can do 3 different things. Which of those 3 different things should you do? Well, the one that minimizes the charge. How do we know it minimizes the charge? Well, is it charged? What is the atom holding the charge? Is its size different? Is the electronegativity different? Is there resonance? Is there induction? You're using those exact same rules every single time you run a reaction. So this goes back to that whole idea of Lewis versus Bronsted-Lowry. We are using these in a Bronsted-Lowry context, but they apply to all reactions. Okay? Cannot stress the importance of having those rules and applying them appropriately. Okay? To apply, what are you applying them to? The definitions. So you have to know what an acid is. You have to know what a base is. Okay? Make sense? Enough? Okay. Could we quantify it? Yes. So if we take a look at this reaction, we're taking the compound benzoic acid and reacting it with water. Okay? So benzoic acid will likely act as an acid. Okay? So we could probably already predict that and know something's going on with it. Okay? But we could, if we don't know, run both reactions. Have it act as an acid, have it act as a base. And the top reaction, what did benzoic acid act as? How do you know it acted as an acid? When we find its conjugate partner on the other side. We've noticed that it has lost a hydrogen. That means it acted as an acid originally. Ooh, that's fun. I have lost connection. So I'm going to keep hitting the reconnect button and hope it connects, because otherwise we've lost our video recording. Maybe we're back. Is that writing?
Yeah.
Okay, maybe we're back. So we're saying it's acting as an acid. What about the bottom case? How do you know it acted as a base? We find its conjugate partner, and what changed? It accepted a hydrogen. So we're looking at it acting as a base. And arguably I picked the wrong oxygen, but don't worry about that. Okay? So we can now say between those, how do we decide what's going to happen? Well, if we look at minimizing charge, we compare the charge. The top reaction, how many species are charged in our products? 2. And the bottom? 2. Shoot. Okay? So what are we saying when we're minimizing the charge? What are we looking at? Stability of what? Of the charge. Which charge? The reactive charge. Which is more reactive, a negative charge or a positive charge? Great question. Yes, they're both reactive. Which one is easier for us to interpret? Okay. Typically it is the negative, because what are we moving when we do a mechanism? Electrons, and electrons are negative. So we can evaluate how those electrons shift around by looking at the negative charge. The positive charge does not help us quite as much, because we're now kind of doing hand-wavy things. We can't move stuff with a positive charge. We just have to deal with it as is and do whatever interpretations we want from there. The negative gives us a little more freedom. So what we can do is compare the negative structure in both reactions. So on the top one, our negative structure, I now have boxed. In the bottom one, there's our negative structure. Which of those negatives is more stable? Because? So charge, are they both charged? Yes. What's the atom holding said charge? Oxygen in both cases. If we move to size, is there a size difference between oxygen and oxygen? No. Is there an electronegativity difference between oxygen and oxygen? No. The next rule is resonance. Do we get resonance for either of these? We should recognize that we can draw a resonance structure for the top one. And again, where the focus needs to be is on the atom that's causing it to be charged. I don't really care about resonance within the benzene ring, because it's not affecting that negative charge. My electrons have gone into a pi bond. The electrons have now gone into the structure, which then means they are less likely to act as a base, because to act as a base, where must the electrons go? Away from the structure. By drawing an option for them to do anything other than go out, we're showing it's more stable. That is our resonance effect. If we look at the hydroxide, can I have those electrons go into a pi bond? No. So there's no resonance for the bottom one, there's resonance for the top one, which suggests which of those two reactions was more valid? The top one. Do I have that animated? Oh, I just deleted it. That's fine. So we say the top one is more likely to go forwards. Does that mean it will go forwards? Not necessarily. How do we decide if it will go forwards? We can go through and compare charges, and that again becomes difficult. Here we've got charges in the products, but no charges in the reactants, which would suggest we don't really see anything. We probably say no real reaction happening here. Right? To quantify, what would we need to look at? What numbers? The pKa. We could look at the Kas, okay? But pKa is typically easier to compare, and we aren't looking at, well, officially we are looking at the pKa for the whole thing. What we would do is look at the pKa value for each of our reactants. Benzoic acid has a pKa of about 4. Water has a pKa of about 15.7. Which one is more acidic? benzoic acid, right? Because it has the smaller pKa value. That would suggest that benzoic acid should act as an acid. We don't have to do charge comparisons. We have the pKa's. We go through and look at the product. Which pKa do I want to look at for the product? Conjugate acid. Why do I not look at the conjugate base? Because it's a base. It's a very good answer. We're comparing the pKa's. I don't want to look at the pKa for a base because it's not an acid. Which one is the acid? The correct one? Yes, the correct one is the acid. Oh, the rightmost structure one. Yes. Because it has an extra proton. We could do that. What happens when we shift across? You could say it lost a proton. I like where you were going over here. I believe that was you, Wyatt. It has a positive charge. Looking for those charges can help tip us off to our acids and bases. What is the pKa for that species? 13. They were valiant attempts, Nolan. You're at least attempting. That is a step above. It is negative 1.5. Which is the stronger acid? The right side is the stronger acid, which means which way does our equilibrium favor? The reactant side. Very little of it forms product. Almost all of it goes to the reactant. So when I add benzoic acid to water, virtually nothing happens. Okay? So we can use those pKa's to help us out. Okay? If we wanted to look at the equilibrium constant for this reaction, that's the power of 10 to the difference in pKa's. Okay? There's one question in the smart work on it. I don't like numbers, so I don't get into dealing with the KEQs, so don't stress about that. But that's what's happening within it. I won't ask a test question there. Does that make sense? So we can quantify using numbers, but to do that, what did we need to know? We needed to know the numbers. We have to have those pKa's memorized. So we could go through and use the rule sets that we just talked about, those 6 rules, starting with charge, then size, then electronegativity, then resonance, induction, hybridization. Okay? So we can apply those rules in most cases. Not all cases work out perfectly for us, but it gets pretty darn close. Okay? If we're asked to quantify, then we need pKa values. Okay? We could bring in all sorts of equilibrium constants and products and reactants and all sorts of fun stuff, which you already know from 152. Correct?
Yes.
Correct? Correct?
Yes.
Thank you, because I don't want to teach it. Okay? Ultimately, the big conclusion we need to get at is pKa. A big pKa is a weak acid. Small pKa is a strong acid. That's really all I want you to get out of it. Okay? Which gets us to the next part. You should go through and memorize your pKa's. Acid-base chemistry, as in the Bronsted-Lowry definition. We're still getting questions on Lewis. The acid-base Bronsted-Lowry definition, those types of reactions are super, super common. They show up pretty much everywhere. So it is helpful to have those pKa's or some pKa's memorized so that when you see a reaction, you can be like, yeah, that one's likely to happen because of the pKa imbalance. Okay? So for pKa's to memorize, these are the ones I would highly encourage you to memorize. Okay? So a carboxylic acid has a pKa of about 4. Alcohol, about 15. What did I say water was? 15.7. 15.7. What is an alcohol? What is the difference between an alcohol and water? Carbon. Carbon. So water fits under the alcohol moniker for our pKa memorization. If you just nail 15, you're close enough for both. Phenols, pKa of about 10. Alkynes, 25. Amines, we'll come back to. Alkanes, 50. Alkenes, 40. Water is both neutral, or is our standard neutral. It can act as both an acid and a base. So let's take a look at the alkane at a pKa of 50. Which is more acidic? Water or the alkane? Water, because it has a lower pKa. Because the alkane has a higher pKa, does that mean it's a stronger base than water? Good. No. pKa's rank acid strength, not base strength. Just because you have a higher pKa doesn't make you a stronger base. It means your conjugate base is a stronger base. Okay? So we have to be careful with that referencing. Remember how we talked about up on the board, the alkyne is more acidic than the alkane. Alkane at 50, hybridization at sp3. Alkene hybridization is sp2. What happened to the pKa? It got dropped. Got dropped? It's lower.
There you go.
Okay. It's lower by a factor of 10 because this is now on a log scale, that's 10 to the 10. How much more acidic is it? A lot more acidic. Compare that to an alkyne. Drops to a pKa of 25. Your alkyne is drastically more acidic. Right? Is it more acidic than water? No. Okay, so even though that is more acidic, that does not make it an acid. It's all about what you're comparing it to. Kind of make sense? Okay. pKa's, again, I'll state, you should go through and memorize these. The reason why I have to say should is I have never memorized these. Okay? So it is not a requirement to get through the class. I think it just helps in a lot of cases. There have been plenty of times where going back and working on a question, I'd be like, oh, that reaction totally goes because of the pKa's. Oh, crap, that stupid OChem instructor that I had in San Diego told me to memorize the pKa's was right. What a jerk. Okay? Same thing can happen here. You don't like it when somebody's right. The one thing to watch out for is amines. Take a look at amines. You'll almost always, when you look them up, that's starting to change. If you look at an amine, they almost always report the pKa for an amine at 9.
So it could be 35 or 9?
What is the 9 in reference to? If it's a 9, what does that mean? Acidic or basic? Acidic. How do you know it's acidic? pK then what? Water. That's how we know. So if we're deciding is it acidic or basic, the basic was a bad one to throw in there. If we're deciding it's acidic, we're comparing it back to water. What happens when we add it to water? Well, if it's a pKa of 9, what happens? Well, the solution becomes acidic. What's the hydrogen removed to make the solution acidic for a pKa of 9? If it's from water, then it's not the amine acting as an acid. It's that hydrogen. That hydrogen is the pKa of 9. Wait, where did that hydrogen come from? Because that wasn't there before, was it? Oh, no, it wasn't. Mike had to erase something. That's because nitrogens typically are not acidic. They act primarily as bases. So when we look at the pKa of an amine, everyone's like, well, it's a base. So if you're looking for the pKa, you must be looking for the pKa of the conjugate acid of the amine. That is the pKa 9. The one that is 35, the 35 is one of the hydrogens directly connected to the nitrogen. Is that acidic? No. That's 10 to the power of 15 less acidic than water. Okay? Really, really not acidic. Nitrogen typically acts as a base, not as an acid. So be careful when you look up your pKa's because the pKa's don't necessarily match when you're looking at that one. Okay? Leveling effect, it's mentioned in the textbook now, so we should mention it now anyway. It's really a big role in Chem 236, and it's usually a big role or a big player around everybody's least favorite functional group, the amines, because the amines have this kind of dual characteristic of acid bases, and they tend to mess with students entering answers. If we're under acidic conditions, the amine acts as a base, so we wouldn't expect to see the amine as a product. It has to be protonated. Okay? That's what's happening here. If I'm under acidic conditions, so I take water and I add HCl to it. So I'm running a reaction in water and I add HCl. Do I have water? Not really. I have H3O plus. Did I have HCl? Not really, because HCl is such a strong acid that it reacts with the water first to form H3O plus. So if I'm doing a reaction in water, I should never have HCl react with the main stuff, because it's going to react with the solvent first to create a secondary species. The secondary species can then react. Okay? It is such a small, nuanced effect. It's not a major issue to watch out for. We'll talk about it a lot more in second semester, okay, and try and directly state it. Most courses I've seen never reference the leveling effect. Okay? They just kind of assume it's there and you have to watch out for it, which is kind of irritating. Okay? But all we're saying is that if we're in a strongly acidic environment, that means we cannot have bases. Because I'm in an acidic environment. If I'm in a strongly basic environment, I cannot have acids. That's it. What would the charge be on my molecules in an acidic environment? Why positive? Because it's an acidic environment and hydrogens are positively charged. What charge would I never expect to find in a basic environment? Positive. Yep, I switched the question on. We would never expect to find a positive charge structure in a basic environment because our basic environment is negatively charged. It's going to remove all positively charged structures. So when looking at a mechanism, we have to evaluate what conditions are we under. Don't show that one because it shouldn't show up. So you may have to tweak your mechanism to account for that. Again, a much larger issue in second semester. We could also go through and look at thermodynamics, products, reactants, all this kind of fun stuff, KEQs, super exciting. The big one to get at, if your delta G is less than 0, the reaction is a spontaneous reaction, also known as exothermic. Our products are more stable than our reactants. So if I was to draw a reaction or an energy diagram, here's my reactants. Where would my products be for a delta G less than 0? My products must be lower. So I'd be looking at something like that. What if I had a delta G that was positive? It is non-spontaneous, and my product energy would be higher, and I'd have an endothermic reaction. Endo, exo, spontaneous, and non-spontaneous. Kind of makes sense? So there's all our fun stuff. Entropy does show up, though a little less frequently, and again, more frequently in second semester than in first semester. Okay. Entropy is our delta S, and enthalpy is H. If our entropy is greater than 0, then that means we have more motion. Our particles are moving more. So we could add heat. Well, that has nothing to do with the reaction. That has something to do with us doing heat. So how would we see a reaction that had more entropy? $152 was only like last semester, 2 years ago. More disorder. Why is it having more disorder? Why look at a reaction? How do you know the entropy went up? Could look at phase differences. Almost all of our phases in OChem are in the same phase. We're almost always in solution, usually an organic solution. So phase doesn't help. Temperature is something that we would change, so that doesn't work. It can, not necessarily, because that ties back to the balance between H and us. Right idea. The amount of our species. Do we have more products, less products? Okay, and not just in general, but the number of particles. If you have more particles, that means more entropy. There's more possible states of motion. If we have less particles, we have less possible states of motion and our entropy goes down. Okay? This diagram, in my opinion, is how 152 should end. Okay? This is everything that you did in 152 is in this diagram. Okay? I said, well, that's not that big of a deal. There's not that much. There's so much stupid information in this. We've got reactants. We've got products. We've got Gibbs free energy. We can look at thermodynamics. We can look at kinetics. We can look at activation energy. We can look at transition states. There's tons of information buried within this graph. Okay? Is this reaction as shown likely to occur? Why? Why is it exothermic? How do you know it's losing energy? Products are below the reactants. Okay? So by looking at this, we can start to draw conclusions about the likelihood or the validity of an individual reaction occurring. Okay? Have we done this already? Yeah, we did. We just talked about an acid being stronger than another. How do we know it's stronger than another? The product energy is lower. Okay? What does that mean for our energy diagram? What would that look like? Okay? So if we took a look at this reaction, what would we expect to have happen for our energy diagram? Well, it's only one reaction, so how many humps are there? One. So we can draw. There's a hump. Okay. Do I know the energy of either my reactant or product?
Yes.
What is the energy for my reactant? What is the 80? It is a change in energy. Do I know the energy of my reactant or product? No. All I know is the change. So I can't establish and say the reactant is at 42 kilojoules per mole. Okay? But what can I specify? That's a positive value, which means, what's that? The products are higher in energy than the reactants. There's my reactants, there's my products. How much higher are my products in energy? 80 kilojoules. Is this reaction likely to occur?
No.
Why not? Products are above the reactant, meaning it's endothermic, meaning non-spontaneous, non-spont, less stable products. So we could go through and quantify this. You might say, well, you were talking about all these rules and extra things. What is the charge on the reactants? What is the charge on the products? Okay. We have a positive and a negative. The overall charge must be neutral because it started neutral. But I now have charges in my structure. What does that mean about its stability? It's less stable, so I would expect the energy of my products to be higher in energy than my reactants. Oh, crap. That's exactly what the energy diagram shows. We can't quantify that energy difference by looking at our reaction. We can ballpark it. Okay? And where Gen Chem gets all superior, and, well, maybe they aren't superior, is saying they've got all sorts of numbers and they can quantify stuff. That's really cool. You can quantify this reaction, okay, or further reactions. And it takes days, but you'll get it exactly correct and you'll be right. Or an organic chemist can sit down and within probably a minute, they get the exact same answer without having to use a supercomputer. This is why organic chemistry trumps Gen Chem. It removes the necessity for numerics, and we can start to make quick approximations. Those approximations we can make faster than a supercomputer can. That's why we do OChem. Okay? Oh, look at that. It went up in energy. Amazing. Except their picture looks prettier. Okay? So relative acidities. Could we use an energy diagram to look at relative acidities?
Yes.
Okay? So if we start off our energy diagram for both these reactions, take a look at this. What are we assuming those are going to be acting as? Why them both acting as acids and not as base?
No, methane acid
Okay, so here's an interesting point. I'm saying we're looking at methane acting as an acid and ammonia acting as a base. While that is technically a true statement in a reaction, what does it say between those two? Versus. So what am I trying to do? Compare them. Should I compare acids to bases? No. If I'm doing a comparison, I need to make sure I'm comparing the exact same thing. So now the question, because the ammonia will typically act as a base and the methane will typically act as an acid, which one will switch? Should I look at methane as a base, or should I look at as ammonia as the acid? Why ammonia is the acid and not methane as the base? Fair enough. I can accept you reading the slide. It says we're comparing acidities. Try again. Give me more. For methane to act as a base, what does it need to have? Anybody see any electrons on the methane? No. Methane can't act as a base. Okay. So we're looking at both those acting as acids, which means water is acting as a base. We go through and run the reaction. What do we end up with? H3O plus in both cases and CH3 minus and NH2 minus. If we're to put this into an energy diagram, how many steps? So that's a tougher question. How many reactions are being run? 2. For each reaction, how many humps? 1. So we might expect 2 humps on our energy in our diagram, but we're really only doing 1 hump. So it's 1 hump per reaction. And we'll call this our purple reaction, and we'll do our green reaction. Reactants. Do I see any large differences in energy between the reactants? Said another way, do I see any large differences in energy between the products? Yes. Why are you saying yes? Lone pairs. We see negative charge. Is there a difference in energy between negative charges? Yes. Those are very highly reactive. Let's take a look at the reactants. Do we see much of a difference? No. Why? They're all neutral. Okay, so we would predict that those are very likely starting at the same energy. Okay, at least as a first approximation. Okay, they are both going to go up in energy. So we'll go up, we'll turn. What do I expect to see? Which one is going to be the highest energy? The NH2 I'm hearing is the highest energy one. Which then means your methane is the lowest energy, right? So our negative carbon is lower in energy. If it is lower in energy, is it more stable or less stable? It's more stable. So carbon can hold a negative charge better than nitrogen. Oops. Carbon is going to be the top one. Nitrogen will be lower. Okay. So if we look at a purely thermodynamic level, what do we say? Well, which product would we expect to see in larger concentrations? NH2 minus or CH3 minus? NH2 minus because lower in energy. There's a little rule called the Hammond postulate. And it used to confuse the crap out of me, primarily because they used a name with it. Okay, but let's just list out what the rule means. Your transition state, which is where on this? It's that peak. Your transition state for any reaction will be closer in energy to the reactant or product that is closer in energy to it. What does that mean? to the reactant energy? Which is closer in energy to the transition state, the products or the reactants? The products. So I would expect the transition state to be closer in energy to one of those. It'll be closer in energy to the product than the reactant, which is already kind of what it's showing. But the power here is that we're saying if we compare these two, that purple line is higher as a product, which means its transition state energy should be higher than the green one, which means what happens to the green line? It shifts down a little bit. What does that mean for us? It is easier to get to, which then means stupid connection. More likely. So we get two effects contributing to the nitrogen being there, our primary product. One, it's lower in energy, and two, the transition state is a little bit lower in energy. How much of an effect is that? Well, it depends on each of the individual reactions. Okay? The transition energy is dictated based on orientation, speed, size, all of these fun little things that feed into it. And when we look at an acid-base reaction, how much different is the orientation for this comparison? Not really different. How about the size? Nitrogen versus carbon? Not really different. So there aren't a whole lot of differences here, which means when we go through to look at our energy diagram, we don't see a huge drop, but we do see a drop. Okay? And that's what this is trying to show. Notice our amide being more stable is lower in energy than our carbide. Okay? So we're using energy diagrams to dictate what happened within the reaction by evaluating those charges. It's just another way to represent the reaction. Notice they both started at roughly the same starting point because they were neutral. Okay? Our difference only really appears when we generate charge structures. Make sense? Okay. Ion stability. Okay, one of the things that we talked about here was negative charge. Back when we talked about mass spec, I glossed through the other half of this slide. Okay, but now what we're looking at is negative charge. Why are we looking at negative charge? Why would that now be relevant to be discussing? What are we comparing when we decided which one was higher or lower in energy? What charge? The negative charge. So we can look at differences in electronegativity, we can look at size, we can look at hybridization, we can look at all of those things. What happens when we move to a situation like this? What atom is holding the charge? Carbon. Do they have a different charge? No. Do they have a different size? Do they have a different electronegativity? Still carbon. No. Do we have a different resonance? This doesn't have enough information to say we have resonance, which means don't assume it's there, so no resonance. Do we have a difference in inductive effect? Ish. Okay, carbon versus hydrogen, yes, there's a difference in electronegativity, but this is where this one goes really sorts of sideways. Okay? None of those rules really work to explain the stability of this. Okay? What we're going to end up looking for is the difference between these. Okay? So a couple extra things here. We've got a labeling system. I'm calling it zeroary, though officially it's known as a methyl, primary, secondary, and tertiary. What are those names in reference to? The number of carbons surrounding whatever carbon we're referencing. Okay, so in this case, the carbanion. So tertiary means 3 carbons. Zeroary means 0 carbons. I would really appreciate it if you propagated the zeroary term. There's enough old people that are probably saying, no, don't say that, but we should try it anyway. Okay. So, what's the difference? When we start, we go out. What do we have here?
Hydrogen.
I would argue that's not hydrogen. We have electrons. What's in that electron? Or in that bond? 2 electrons. What's in the next one? 2 electrons. What's in the next one? Are those electrons going to destabilize or stabilize that negative charge? Why would they destabilize it? Negative repulsion. That's destable. Okay, cool. So that top one is not stable because there's 6 electrons chilling around that carbon, and that's destroying the negative charge. What's in the next one?
Same thing.
Exact same thing. What does that mean?
Same thing.
They're all the same stability based off, good follow-up, based off of that analysis. They are all the same stability, which means analyze more. Find the difference. If the bond wasn't different, maybe we should move to the atom outside. What's the atom outside?
Hydrogen.
Move out to hydrogen, hydrogen, and hydrogen. What can you tell me about that hydrogen?
Same as all the other ones.
It's the same as all the other ones? Okay, so let's fix that. I'm only looking at that hydrogen. What can you tell me about hydrogen? Why would it have a positive charge? If something was taking the electrons away from it. Is carbon more electronegative than hydrogen? No, so I don't quite accept that. Maybe you could say it has 1 proton. I would accept that as an example. It's not a positive charge.
No, I said one proton.
Oh, I didn't hear you. Sorry. Good job. Thank you, Amanda. You are now permanently on record as having said that. Good job. And 1 proton. So how many protons are in that top one?
3 protons.
3. Move to the next one.
2 protons.
1 proton.
0 proton.
Stop just saying numbers. 1 proton.
I thought you were going down the list to the next one.
6 protons. What does that mean? There's 8 total protons around the primary, and how many were there around the zero area? 3. What do those protons do? Stabilize negative charge. Which of those 2 structures is more stable, the primary or the zero area? Primary because? More protons to stabilize it. Okay? The issue with that is when we show curved arrows, what are we showing the motion of? Electrons. We don't show the motion of the protons. So while this analysis does work, I don't like it because it's not following our standard notation. So let's switch it up. Let's now reference the electrons. How many electrons does that hydrogen come in with? I'll accept 1. It depends how you want to count it. As long as you're consistent, I'm fine with it. How many hydrogens does the next one come in with? And the last one? So it has how many electrons around it? 3 electrons. What's happening in the next structure? 1 electron. 1 electron. And if you're going to count hydrogen as 1, you need to be counting carbon as 6. You could argue the 4, but
Wait, why 6?
how many electrons does carbon have? 6. So that means how many electrons?
8.
Actually, the proton count didn't work. That's interesting. Yeah, it would have gone backwards. I thought the proton count would have worked. It doesn't. This is why. What do our curved arrows show the motion of? Electrons. Looking at the proton count doesn't help us because do the protons interact between atoms? No, all the protons are doing are repelling away from each other. What interacts first between our atoms? The electrons. We have to use the electrons. Which is more stable, the zero area or the primary? Which is more stable? The zero area, actually. Why is it more stable than the primary?
There's less.
It has less electron-electron repulsion. All right, what happens when we move to the tertiary? How many electrons? I'm just going to trust your number. That sounds kind of odd to me, but I'll accept it.
There's 18. Secondary has 13.
So, of those structures, where is our anion most stable? Zero area. We would expect to find a negative charge, okay, on the least substituted carbon. It's kind of weird. That's the way it works. That's the most stable one. What happens, let's see, if we move to these guys?
It's the opposite.
Why is it the opposite?
Because on the tertiary, the 3 carbons around it can
In the tertiary, there's still, what do we say, 18 electrons? What can those 18 electrons do? Stabilize the positive charge, and we end up seeing the inverse relationship. So a tertiary cation is the most stable. A zeroary or methyl anion is the most stable. Okay? Which brings us to the middle section. What's in the middle? Radicals. What do the radicals most approximate? This is a tricky question. To become an anion, what do they need? An anion, they would need?
More electrons than protons?
How many electrons? More.
One.
One. To become more like a cation, what do they need to do? They need to get rid of an electron. Which is closer, the cations or the anions? It's a good question. Okay. All I got are hand-wavy arguments for you. Okay. To have a fully substituted orbital that requires hybridization, you need 2 electrons. Do we have 2 electrons to make the hybridization of those radicals fully sp3? No. We're missing an electron. So they aren't sp3, they are sp2 hybridized. Which then means, what do they mimic most? The cations. The anions come out as sp3 because of that lone pair of electrons. So our radicals most approximate our cations, not the anions, as far as their reactivity goes. Which means a tertiary radical is the most stable. Just like a tertiary cation. Okay? To do that analysis, we have to follow through the electrons. And that is our explanation behind it. We can't use the protons, which we started with initially. That was bad on my part. We got to use the electrons. Okay? Do you need to derive it every single time? No. More than likely, it makes sense to just memorize that your tertiary cations are more stable than your tertiary, or than your zeroary cations. Okay? Zwitterions, again, larger effect in second semester. Really, really big effect in biochemistry. What is the structure of that compound? Name of that compound. Anybody recognize it? Maybe we should try it the other way. How many people have taken a biology class? Yeah, everybody that rose your hand needs to know the answer to that question. That is the base structure for an amino acid. You go, oh God, how would I ever? I didn't memorize that. You mean that functional group right there that's known as an amine? And that structure right there that's known as an acid? You didn't recognize that was an amino acid? Those of you from biology, when you write out your protein structures, what do you start with on the left always? It needs to be the amine. Your carboxylic end of a peptide is always on the far right. Why? Because that's how we write it, amino acid. We keep it standard. Yeah, sometimes biology classes talk about it, sometimes they don't. It's just irritating. So, some species will have more than one acid or base functional group. Amino acids are characteristic of this. They have the amine, which is typically a base, and they have the acid, which is, well, typically an acid. So how do we decide the protonation state? Well, the protonation state is going to be dictated based on the pH of the solution. This is why biochemistry really, really cares about pKa's and pHs and all that fun stuff. Because what happens if we change the pH of the body? Bad stuff. We die. Why? If you change the pH, if we start at a neutral pH, here's your amino acid typically, and I make it more acidic, what happens? More acidic means more H+. What does the H+ do? Reacts with the negative charge to become this structure. What did I change? Begins with an I. 2 words. Second word begins with F. I usually abbreviate it as IMF. Your intermolecular forces have changed. So much so that what happens? Your protein changes its solubility. That's not a big deal. Things change solubility all the time. Except in your bloodstream, if you take a protein that was now soluble and it turns into a solid, that's known as a clot, and that kind of sucks. Okay? That usually results in death. So biochemistry is all about balancing that acid-base system, usually through the Henderson-Hasselbalch equation. So if you were asked to decide which state is more populated, the protonated state or the deprotonated state, you'd have to know the pH and the pKa's, and you'd look at this big old long stupid Henderson-Hasselbalch fun stuff. Or, please say it's there. Oh.
No, what happened? Oh, God. Skip like 10. It's just awkward. You should just get up. Oh, it's
Time's up.
Or you would have memorized the relationship between your pH and your pKa's and what that ultimately means. If your pH is greater than the pKa, if a pH is larger, that means we are more basic. We're in a more basic system than the pKa. That means we're in the deprotonated state. If the pH was lower than the pKa, we're in an environment that is more acidic, which means I need to be in the protonated state. No need to do Henderson-Hasselbalch stuff. What we'll talk about on, what is today? Wow. What we'll talk about on Wednesday is we will start moving into substitution. The substitution and elimination chapter has lots of stuff going on within it. Please read it ahead of class. We'll start with summaries, and then we'll look at the nuts and bolts of everything.